All right, the second part of this section is on what we call the work integral. It is also called flow, and it is sometimes called circulation. Circulation, if I can spell it correctly, that's good. Uh, and um, and usually the word circulation is reserved when this curve C is not just a curve, but a loop. It goes from the starts at the same point, it starts at a point, and then comes back to the same point. Then the word circulation, which has the idea of a circle, makes sense. Okay, but before I go into the discussion of this part of this, let me show you what I will be making available to you. So I have a sort of a summarized all of these things, these line integrals in this section in a short essay or exposition or expository paper, I guess. Right? And I'll show you this, but and you'll see this later. But what is a work integral? And I start with this whole idea that it is a continuous addition, and then start with a Riemann sum, and I will explain exactly what that arc length parameter is, okay? And then I will be talking about what ds is, and this is something you've just seen, right? That, and by the way, I wrote this before, ds is equal to the speed times dt. That's how you convert ds into expression using dt. But just focus your attention on this just a minute. This is the distance, right? This is the distance traveled. And what does it say? It says distance is rate times time. It's something you probably heard when you were like in third grade, right? Well, that's true even in infinitesimal sense. This is when you talk about differentials. ds, distance, is equal to the rate times time, speed times time. And so here is how you find the value of the line integral. And then I go into the two important real valued functions. One is f dot t, and that will give you the work, which the work integral, which I will be talking about in just a second. And then the second application is f dot n, which is our flux. And then I will explain what all of these things mean so that you can find all the details which you may or may not need to have. But I will have little, maybe a guide, maybe an optional video on this later. Okay, now let's get back to the work integral, or as we shall we say, let's go to work, since we are going to be talking about the work integrals. All right, so what is that, right? And so we talked about this function, right? And so that is a real valued function. So what kind of applications do we have? Well, first, you can just find line integrals as we did before, but there are certain important things to be considered for this f. Okay, so what are they? This is one of those things. Okay, now I have explained this at the last part of the previous section, but if you're trying to move an object with this force f at an angle theta, okay, there is the this force times the distance is actually not going to give you the work done by this force F along this line, or the motion, the direction of the motion, right? In order to calculate how much force is exerted onto this object in the direction of the motion, which is what you need, the length of this red arrow, or the red vector, is the tangential component of that force F. Okay, so F, capital F, consider this to be the vector field. The length of F is not what we need. What we need to integrate or to calculate at each point, of this motion, is how much of the force F is actually moving this object in the direction of capital T. So that's a tangential component. And let me just go ahead and write that. F dot T gives you the tangential component. Okay, and it has to do with the fact that this length is the magnitude of f times the cosine of theta. Okay, and that's exactly what this is. Okay, just because the capital T is a unit vector. So this is the tangential component of the force F that's moving this box in the direction of T at this point X. Okay, and that this tangential component is defined at every single point of this line or curve, right? So by integrating, you get the entire work done by the force or vector field F in the direction of t. And so that is why we integrate f dot t ds. And we can define this to be the work done by the vector field F along C. Now, it could actually be negative, okay? Because here's the thing. Let's say your C is here, okay? You're going from here to here, and maybe the plane is flying from point A to point B. And if the wind is, maybe the better illustration is a sailboat, okay? Because sailboats don't have, the jet engine, it has no engine. If a sailboat is just sailing, and then the wind is blowing like, like this, um, that's nice. And then maybe it's, sometimes it's backwards, okay, but then mostly it's forward. And by the way, the sailboats can actually go in opposite of the direction of the wind. But anyway, so the point is, if the wind is blowing, described by this vector field F, as the sailboat goes from A to B, the work done by F, the force field, which in this case is the wind, as the boat goes from A to B, is described by, like how much of F is pushing this boat this way, how much of the boat is pushing this way. So at each point, you are calculating the tangential component. Okay, in other words, the component of F in the direction of the motion, and we are adding all of these tangential components at every single point. That is exactly the idea of the integral, right? So this, if you integrate it over C, is the work done by F along C as the object moves from A to B. That is that's really the summary of the work or the flow or the circulation integral. It turns out, by the way, this is actually a little easier to calculate. So let me show you why that is true. Okay. Here is the sort of clever thing. Okay. So you will find out that you don't actually have to find the speed in this case. That speed is the magnitude of r prime. All right. Let me show you why. All right, so the question is, how do you evaluate this work integral? And to our surprise, okay, this time you don't actually need to calculate the speed, which is the square root of x prime square plus y prime square. How can this be? Because I just said this is equal to this thing times dt, right? So let me show you. This is actually really cute, I think, right? So we need to calculate f dot t ds. Let's go ahead and write this, okay? Now, f dot tds is f dot, okay, how do you find t? What is capital T? You remember? It is the magnitude, it is the derivative, which is the velocity, divided by its norm, right? Because that's how you normalize it to make that into a unit tangent vector, all right? So that's what this is. Now, remember what I said about ds? Yeah, at first I said nobody likes ds. Poor guy. So, so what's ds? What did I say ds was? You can write ds in terms of, yeah, ds over dt, right? And so this turns out to be the speed. What is speed? Well, yeah, you got it. I think you got it, right? When you take this, and then ds over dt is the speed, which is the magnitude of r prime itself. You see what's happening here? Like, man, this is almost too good to be true, right? You say, wow. Yeah, you can stop. You can actually pause your video right now, stop and reflect, and just imagine how incredible this is. Okay, this is just maybe like too beautiful to be true, right? Because what you see is, look, you can cancel, right? So what do you have to do in order to integrate f dot t ds? Well, it looks like you just take the dot product. Okay, so let me go ahead and write this down. So this turns out to be f dot r prime, and that's it. Okay, and that's why I said you don't need to calculate this. You take the dot product of the vector field and r, not r, but r prime. Okay, this is really good. This is really good. So let me write what I just said in red. Okay, so the work integral flow integral, circulation integral is this. It's the integral over C of f dot t ds. Okay, by definition, the work integral is this because you are integrating the tangential component of the vector field f along C. But to calculate this, what you have to do is remember, I should write this down, where C is parametrized by RT, where T goes from A to B. Okay, and because I have to tell you what A and B is in order to say something like this, it's the integral from A to B of f dot r prime derivative of r, that's the velocity, right? And this is going to be a real valued function, dt. That's it. It's really simple, right? And because this is a dot product, okay, watch this. Because it's a dot product, sometimes people even write this as f dot dr, okay? So this r prime dt is sometimes abbreviated with d with a vector r. Okay, so if you see this expression, now it's easy to remember this because this sounds like one of those past presidents of the United States, right? You see that? FDR, okay? So FDR is associated with creating, he had a thing called a New Deal, and he is credited with providing or creating lots of work, okay? So the work integral, of course, has FDR in it, right? And so the work integral can be written as f is the vector field, dot dr, okay? FDR associated with work. All right, so let me give you an example. Again, no need in this case, if you're trying to find the work integral, evaluating a work integral, you don't have to um, calculate the speed. You do have to calculate r prime, okay, and you have to dot that with f, but you don't have to find the square root of x prime square plus y prime square. Okay, let's do an example. Let's say f is a vector field, 3y minus x, comma, y squared. Remember, this is the first component, this is the second component. And C is a line segment from 0, 0 to 2, 6. Okay, so find the work integral. Find work, which is the integral of f dot t ds. And it turns out you don't really see f dot t ds anymore. I mean, this definitely is the definition of the work integral of f, how much work is done by f along c. That's the question. And it makes sense to integrate f dot t, which is the tangential component of f. That's a real valued function. But often people just evaluate f dot dr, which is the same thing. And it turns out there are other expressions of this, which I will write in a moment. Okay, but for right now, let's go ahead and do this. So the curve goes from 0, 0 to 2, 6. It's like this. I am just drawing a very rough sketch. This is my C, right? How do you parameterize this? Let's parameterize R as T 3t because the slope is 3, and of course t should go from 0 to 2, right? Okay, and f, oh yeah, so f can no longer be written in terms of x and y. Remember, this is x, right? Because I am parameterizing all the points on this curve or line segment from 0, 0 to 2, 6 as t comma 3t. The x coordinate is t, y coordinate is 3t. So f can be written not with, or should be written not in terms of x and y, but y should be replaced by 3t and x should be replaced by t. All right, so y squared is 3t quantity squared. Let's simplify this. This is 9t minus t, which is, did I say 90? Yeah, 9t minus t, which is 8t, comma 9t squared. no problem here, right? All right, so at this point, and then you can do r prime because you know that's something else I have to have. That's 1, 3. And guess what? Yeah, maybe I can just go ahead and do the therefore thing. Yeah, let's erase this. And I see basically I have all the ingredients I need to calculate my line integral at this point, or the work integral at this point. Okay. Remember, I am not integrating like a real valued function lowercase f. What I'm integrating is f dot t, okay, which is a real valued function. And when you integrate f dot t, then you do get the work integral. All right, so the work integral f dot t ds is basically from 0 to 2 of the dot product 8t dot 90 square, I'm sorry, 8t comma 90 square dot 13 dt. Notice here, I didn't have to do this, okay? I didn't have to do this. It's very important for you to remember that. I mean, the speed, of course, this is a square root of 10. That's easy to calculate, but you don't need to do that. You just have to take the dot product of this. This is the nice thing about the work integral. To find the work integral, you have to work less than just simply a line integral, which is ironic because this is called work integral. All right, so this is what, 8t plus 27t squared. Remember, this should be a real valued function at this point, right? 8t times 1, and then 9t squared times 3. So this is what you have to integrate. That's now a calculus 1 question, right? So this is 4t squared plus, what do you get, 9t cubed? And then from 0 to 2, when you plug in 2, you should get 16 plus, what is that, 72? And that would be 88. And that is the work done by this vector field F. Where's my F? So this vector field F is like the wind as a boat goes from 0, 0 to 2, 6 along a straight course. And the force field, or the vector field F, is doing the work, which amounts to 88, whatever the units are, as the boat goes from 0.00 to 0.26. Okay, so that's what it means. All right, so I said there are different expressions, different ways of writing that thing. Let me explain this because you will see this a lot, okay? And even as we go on to the new sections where we use this extensively, by the way, this line integral, and in particularly the work integral, we will use these different ways to denote this same integral. All right, so let f be written as pq. Right, well, often we do that, right? P is the first component of the vector field and Q is the second component of the vector field. All right, now remember, R prime can be written as, what is that? It's dx dt, dy dt, right? That's what this is, okay? So instead of, so let's say R prime dt can be written as dx comma dy. I hope this makes sense. Well, this is just another way of writing this, because if you have dt at the end of this like this, that's what you have here. The dt's will cancel, and so this is just another way of writing that same thing. All right, so with that background, the work integral, circulation integral, or flow integral, by definition, it is the integral of f dot t ds. Remember, the tangential component of f is what's integrated. I also already mentioned this can be written as fdr because this last part, tds, is basically that, okay? Also, now this is a new thing, it could also be written as, because f is p comma q, and dr, well, what's dr? That's this. I guess I forgot to say that. Dr is another way of saying the r prime dt. So this can be written as dx dt, dy, And I'm not a big fan of this expression, but people use this all the time. Many times it's written as pdx plus qdy because that's what you do when you add these. And by the way, remember here, dt disappears. dt is already included in this expression. So no longer ds or dt is here. There's nothing at the end of this. And so it's okay to write the work integral as the integral of pdx plus qdy. See, what I don't like is, like this whole thing, they don't even use parentheses. So it doesn't look right to me, but it is, again, one of those things that somebody decided this is one way to denote this. And I can go back in history to fix somebody's problem or error. So this notation stands. Okay, so this is what we call the work integral of f over c. All right, so the next thing we have to do is to do, maybe I should do another example. I'll tell you what, I'm going to give you a problem by adding one dimension. Okay. So remember all of these things because we'll be using all of these different ways to express the work integral. All right. So I'm going to give you, before I go into the flux integral, let's go one dimension higher. Okay. In R3, what does it look like? Okay, so let's do an example here. Let's say my vector field F, maybe it's the wind or, the way the heat is moving in space X, Y, Z or something. You have P, Q, R, right? That's the vector. This is a three-dimensional vector field. And C, the curve, is described in terms of X, Y, and Z. So if you are given this, then what is that? Then the work integral would be, of course, f dr, right? And that can be written as p dx plus q dy plus r dz. Okay, that's another way of writing that. And so, of course, this whole thing is basically saying you just take f and dot that with x prime, y prime, z prime. That's all you have to do. Okay, so with that in mind, why don't you try this? I am going to give you this vector field f, which is 2x, comma, 2y, comma, 1. Okay, and find the work done by f on an object moving along C. And C is this helix. Remember what the helix is? Not felix. Okay. Cosine of t, sine of t, and t. Okay, so this is a classic one that kind of goes around like this, and and let's say that t goes from 0 to 2 pi. So it's one complete circle, going like this, okay, along a cylinder. All right, so I think you can do this. All right, this is easy. Just use this, and when you think you are done, come back and we'll verify that you're correct, and then we will go into the flux. All right, so I hope you have done this. Basically, this is what you need. All right, you need to find the work integral, which is f dot dr. Right, remember this is just f dotted with r prime. Okay, so that's all you have to figure out. Let's try to find this. Okay, this is what you need. And once you do a few problems, I think you'll get really used to this very quickly. I don't think you'll find this very difficult because unlike the first case where you had to find r prime and the magnitude of it, which is usually messy because it involves square roots, okay, this time it's just a dot product. Remember what I said about dot products? The very first time I introduced you to my favorite friend dot product, I told you, you have to get to know dot product. It's a really nice person. And I said something like, this is just an incredible, it's very simple and it's very useful. Okay, so here we are, a few months later, we are discovering again that dot products are really, really nice. The more you spend time with this product, the more you like it because it is simple, it's not messy, and it is extremely useful. All right, so f dot, so let's write f. Okay, f is 2x, 2y, 1. But remember, what's x? Well, this is my, x coordinate, this is my y coordinate, this is my z coordinate as the object moves from 0, 0, 0, 1, 0, 0 in this case to 1, 0, 1. All right, f can be written as 2 cosine t, 2y is 2 sine t, and 1 is just 1. Okay, what's the derivative of r? It's negative sine t cosine t and 1, right? So let's go ahead, since I need a dot product, let's go ahead and just dot these. Okay, so you get negative 2 sine t cosine t plus 2 sine t cosine t plus 1. That is, my friends, just 1 because the first two terms just cancel with each other, right? Wow, look at that. You don't even have to work to get work because FDR, the integral of FDR turns out to be the integral from 0 to 2 pi of 1 dt, which is 2 pi. Okay, now this is a work done by this object. Now, this vector field, I don't know if you noticed this, but this vector field actually goes, how should I describe this? This point is, the beginning point is 1, 0, 0, right? At this point, this vector field is 2, 0, 0. That is perpendicular. It's always kind of a moving or like perpendicular to this helix, if you remember that. So really, there's no work done because the tangential component of this vector field along C is 0. Okay, well, it's not 0 except this one here. Okay, 1 is a constant motion. So it's pushing, and as this is moving around here, the only component that matters, or it's actually doing the work, is the last component, 1. And it's pushing this object along this curve up to the next point, which is, actually it doesn't end at one point. This is 1, 0, 2 pi. That's the end point. And so the work done is 2 pi. It makes sense that it's positive. All right. So I think that concludes the second portion of this. Now, when you come back to the next segment of this video, we'll be talking about flux integrals.